Alright, in this video we are going to talk about functions. What are functions? How do we test for functions? And get into some properties of functions and their domain and range. And this is going to start our little review of a little bit of college algebra. This is probably covered quickly in college algebra, so it's very good to go over a review of this. But let's actually just first of all talk about a function and get to a definition. A function is a process that associates each element x of a set x to a single element emphasis added there, to a single element y of set y. So, a lot to kind of unwrap here a little bit. The x, which is going to be part of a bigger set x, is going to get mapped to a single element y of set y. So our domain is going to be that set x. So the domain is generally given to you as the x-axis. In classes that apply this would be our independent variable, and our range would depend on our domain. So the range is going to be the set y. Now these elements are, for our sake, going to start off with just the numbers. And we're going to use some non-number elements here to show some examples of functions, but the single element that I added here was really the way that we're going to test for a function. And the test for the function is taking this definition and kind of changing the wording just a little bit to this. For every x, there is at most one y value. Now that kind of brings this idea of single element, because that means x goes to one value of y and not more than one. Now I do put this at most because there are some cases that you can just have an x value that doesn't map to a y value. I mean, again, this is possible in some set theory and some other applications. But for us, we're always going to have an x and a y value since we're going to be dealing with two-dimensional coordinates. But I just wanted to throw that in there at most, just because we are only going to have this up to one y value for these examples. So let's take a look here. If we look down at our first example, we're going to actually work with some word problems. Now it says here, in the problems, determine whether each relation represents a function, and for each function state the domain and range. So if it's a function, then we have to do a little bit more work, and if it's not a function, we can just say not a function and end. So in this situation, our domain is going to be our list of fathers, and our range is going to be our list of daughters. So Bob has 2 daughters, John and Chuck both have 1 daughter. Is this a function? And the answer in this case is no, it's not a function. Because for every x, there is at most one y, and in this situation, Bob goes to Beth and Diane, and therefore this is not a function. Every x has to go to at most one y. So if we look at the level of education and the average income given in this table, you can see that this is a function. Yes. And it's a function because every x value, every element of the domain, goes to an element in the range. So our set x, now that we know that this is a function, I do have to state the domain and range. So I'll do a D with a little colon here, and I'll make this little set notation bracket, a little curve, and I'm going to put my elements in my domain into this set. So less than 9th grade, Let's go 9th through 12th grade. And again, I'm just using some shorter ways to mark this off here. High school graduate, just abbreviate that. Some college and college graduate. All right, there's my set, and I use that little curvy bracket at the end there to show you my domain. Now it's time for range. The range are going to be numbers 18,120 separated by commas. I'm going to kind of not write the comma there just because it'll get a little bit more confusing if I do so. $23,251, $36,055, $45,810. Why does it do that? And then $67,165. I think I can get rid of that if I just... There we go. Alright, so now what I need to do is I need to look at these more numerical examples, the examples that are a little bit more germane to your homework here, and see if these coordinate points, these 4 coordinate points on the left here, are a function. So the rule is for every x value, there's exactly one y value. So -2 goes to 5, -1 with the 6, 3 with the 7, 4 with the 12. There's absolutely no duplicates. So yes, this is a function. Yes, it's a function. Now, I'm going to have to list my domain. My domain is going to be the set of -2, -1, 3, and 4. And my range is going to be 5, 6, 7, and 12. Now, what I've done over here, since your homework's going to deal with, instead of a lot of these concrete integers here, it's going to actually have variables here. These variables, I've picked them to represent these numbers over here, so you'll see that there are no duplicates. So A goes to E, B goes to F, C goes to G, and D goes to H. So this easily makes a function, and you'll note that you will have the same answers to the left and right because I've just given the values on the left, letters on the right. So here's my domain, which is A, B, C, and D, and my range is going to be E, F, G, H. All right, so there we go. Separated by commas, there's my beautiful set notation. Okay, so now let's take a look at this. 0 and 4, 1 and 5, 2 and 5, 3 and 7. Now you've noticed that the 1 and the 5 and the 2 and the 5 share a y value. Now remember, the test here is that every value of x goes to at most one y. So is this a function if I have 1, 5 and 2, 5? And the answer is yes, because every x has to go to at most one y. You can duplicate y's. You just can't have an x value go to more than one y value. So this means my domain for this problem is 0, 1, 2, and 3, because these are my possible x values in this problem. Now if I go to my y values, this is 4, 5. You'll notice I have 5 again. I don't want to write it twice. And then 7. So you'll notice that my range only has 3 elements where my domain has 4 elements, but since my mapping is okay, where every 1x goes to 1y, it's fine, it's a function. And you can have functions where x's go to multiple y's because you can have a flat line. A flat line is perfectly fine as a function, or the constant function. And we'll see the constant function in the next page here, so I'll kind of save that for later. So you can see right now what I've done is I've given letters to designate 0, 1, 2, and 3 with A, B, C, and D. So my domain is going to be A, B, C, D. And my range is going to be E, F, and G. Notice I didn't say E, F, F, and G because I would not write down the F twice. It's kind of like having a duplicate toy. Ever had that situation when you had a toy and you got, or maybe, you got a McDonald's Happy Meal and you got the same toy you got last week, or you and the other friend in the car both have the same Happy Meal toys. You wouldn't consider having like a new part or another color Power Ranger or Teenage Mutant Ninja Turtle or My Little Pony character. You can see I've been to McDonald's a lot. you would not count that as a second copy of it in your set. You have these three elements of that set, even though you had more than one F. So let's look at this example, number 4. Oh, cool. Got a text. Let me turn that off there. All right, so in problem number 4, whoops. Okay, in problem 4, we have -4, 0, -3, 2, -2, 3, and -4, 4. So you see the first point and the last point have the same x value and have 2 separate y values. This is not a function. And it's not a function because your x has to go to a unique y. And in this case, you can see that -4, 0 goes to 2 places. So here's an example of it in letter form. You see how A and D and A and G, so A goes to 2 separate letters. So no, this is not a function either. It has a problem. So let's kind of scroll down and really investigate this idea of something that isn't a function. So now what I'm going to do is I want to plot these points from number 4 on this graph. So -4, 0 is this point here. -3, 2 is this point here. -2, 3 is this point here. And -4, 4 is this point here. So you see these 4 points. What were the 2 points that caused the problem of this not being a function? Well, it would be the points -4, 0 and -4, 4. Notice where they are. These points are right above each other. And since they're right above each other, they intersect a vertical line. So therefore, a good way to check to see if points or a graph is a function is to see if it passes or fails the VLT, also known as the vertical line test. The vertical line test. So, if it fails the vertical line test, it is not a function. Which kind of brings back problem number 3, if you want to take a look at problem 3 again for a moment. Problem number 3 had 1, 5 and 2, 5. Let's just kind of focus on those points there. 1, 5 would be this green dot up here, and 2, 5 would be this green dot here. If I connected those green dots with a green horizontal line, you can see that it passes the vertical line test. You can have a constant function and still have it as a passable vertical line test. You can't have a vertical line because this vertical line is not a function. Vertical lines fail the vertical line test. And so many other graphs do too. Which is why on the next page, which is pretty cool, the next page we are going to look at some pictures in the book on pages 174 to 175 to determine if they're a function. But this kind of brings up one other test that isn't really emphasized in the book at this time, but I feel like if we cover it now, it will help later, especially when we get to inverse functions. Because besides having a vertical line test, we have something called a horizontal line test. And the horizontal line test is useful in later units to determine if a function is one-to-one. So, important to note that this is first of all establishing if something is a function. Because we first of all have to say, okay, is it one-to-one, and it has to be a function in the first place. So things that are functions and are one-to-one have special cool inverse properties. But this horizontal line test means that the function for every... Now you'll see that this test is going to be the flip of what we said earlier. For each value of y, there is at most, and there's that at most qualification, is at most one value of x. Okay, so we're going to use these pictures on 174 to 175, and we are going to check to see the vertical line test to see if it's a function, and then we'll do the horizontal line test to see if it's one-to-one. So I'm going to flip back and forth since you may not have the book in front of you. The constant function right here passes the vertical line test because you can see that a vertical line can only cross at one point here. So this constant function, this constant equation is a function, but it is not one-to-one because it fails the horizontal line test. So back to here. Yes, the constant equation is a function, but it is not one-to-one. Okay, let's take a look at the identity equation. Well, that not only passes the vertical line test, it passes the horizontal line test, which means we can take an inverse of that very easily by flipping the x and y, which we will do later. So yes, it passes in both situations. It's not only a function, but it's also one-to-one. Okay, let's scroll down gently here for the absolute value function. You can see how it's created by every value of x is rendered as a positive value of y. Positive values of x just stay positive. So there is absolutely no negative values of y here in an absolute value function. So this passes the vertical line test, does not pass the horizontal line test. So the absolute value is a function. It is not one-to-one. Quadratic passes the vertical line test, does not pass the horizontal line test. So again, function, not one-to-one. Cubics pass vertical and horizontal. This point here at the origin, it flattens but doesn't stay flat for more than 1 pixel. That point at 0 is its only flat spot, and then it just moves up from there. So cubics, yes and yes. It is a function and one-to-one. Okay, so let's carefully move down to the reciprocal squared, and the square root function. So the reciprocal function. Reciprocal function, yes, it passes the vertical and horizontal line test. Even though there are no values at the x or the y axis, it still passes all the points in the lines that it exists. So yes, functions can have excluded values, and we're actually going to look at that in the next video here. So then we're going to look at reciprocal squared. Passes vertical, does not pass horizontal. So yes, function, not one-to-one. Square root function passes vertical and will pass the horizontal as well. Even though it looks like this is going to flatten out flat, it never does. It just constantly gets bigger and bigger, faster and faster, but it will never flatten. Much like the quadratic will never go straight up, but it will constantly get wider. So the square root function is yes and yes. All right, let me carefully scroll down here. Let's see if I can get the rest of it in on this page. Okay, I can. All right, and now I carefully scroll down here for cube roots. All right, so cube root only has one left on this page. Okay, so the cubic root passes the vertical, passes the horizontal. Awesome, and that ends our little graphic displays here, so let's put a yes for these two. Yes and yes. Okay, so a couple ways to do problem 15 is because we don't have a specific picture of it. But one thing we can think of is that this problem 15 is a composition of linear functions. The numerator and denominator are both linear. And linear functions, if we go back to problem 6, was a function and was one-to-one. And if we look at the fact that it was a reciprocal function, because we have a numerator and denominator, and reciprocal functions had no restrictions, then this is going to be yes and yes. So then we take a look at problem number 16. And problem number 16 has an x cubed, an x squared, and an x. And a cubic function like this has function properties, because not only did the x cubed, the x squared, and the x, that has absolutely no restrictions on any of those. But the one that gives me a little bit of pause is the x squared, based on the 1-to-1. So with that restriction there, without doing a deeper analysis on graphing, I think I'm going to leave this one as maybe a question mark, because we would have to investigate all values along this, and without actually taking a look at the picture or having that, straight scope in front of me, I'm less likely to kind of set that down. But this could be something cool that you could actually look at and discuss, because you have a situation where the x squared function was not 1-to-1, but the x cubed and the x was 1-to-1. So it's maybe not, you'd probably need to do some more investigation. So I'm not going to be one to put my answer down on YouTube, but this would be something for further exploration. But I do want to put my thoughts and discussions about this one. Y equals plus or minus. That plus or minus is a real interesting addition there, because what we have here is a square root function. And we can see that square root functions back in problem 12 were no problems at all. So let's kind of just remind ourselves, what did problem 12 look like? Well, it looked like this, right? It looked like a function that was kind of moving up in this direction. It seemed to be okay. But see, it's plus and minus, which means that now it has another piece to it, like that. What does that mean? Well, that means it is not a function, even though it is 1-to-1. And with this situation of this being 1-to-1, a property of a function, this is really not very important to us to have something that's 1-to-1 and not a function, because we're not going to really use something like this. Though this might be something important in your later math career to take a look at things that have this kind of setup. But this is definitely not a function because it fails a vertical line test. And circles? What do you think? What do you think about a circle? If you just have a circle, does that pass or fail the vertical or horizontal line test? Well, absolutely not. That does not. Ellipses, circles do not pass the vertical line test or the horizontal line test for that.